Hello, everyone, and welcome to our webinar. My name is Marina Silva, and I'm joining you today here from sunny Harrogate in England. And just so we know that you can hear us, you can see us, please type in the chat, where are you joining us from today? While we wait for that, I'll tell you a bit more about this webinar. So in this webinar, John Bacon, our fired heater efficiency optimization expert, will talk about how to improve the efficiency of a steam methane reformer with the use of ceramic coatings. The webinar will take about 20-30 minutes, and then John will answer all of your questions. You can type your questions in the questions tab on your right. And some housekeeping before we start. We are broadcasting live, and some of you may experience technical difficulties. If you do, try refreshing your browser or switch into a compatibility mode or dial into this webinar to get the audio. And I'm going to post the dial-in instructions in the chat now. And without further ado, over to you, John.
Thank you, Marina. Good morning, everybody, or good afternoon, or good evening, wherever you are in the world. And welcome to the ultimate in social distancing. I'm John Bacon. This is a presentation on what the CTEC division of IGS does for steam methane reformers, or improving the efficiency of them. So let's get into it. We've been around for over 25 years now, but the coatings have been around for much longer than that. We've just been using them in the HPI industries since then. What you see here is just a snapshot of some companies that we've worked for, and we've used primarily ceramic coating technologies to coat the insides of fired heaters, reformers, crackers, call them what you will, both the refractory surfaces and the tube surfaces. In addition to the ceramic coatings, we also offer an online service, a maintenance service, which we call Hot Tech, and that allows maintenance to be undertaken while the unit is still operating and still producing. So you might be interested in a webinar we have coming up shortly, which covers all those technologies. So let's get on to what we do for steam methane reformers. I'm sure you're all aware they're box heater designs. There are various different designs of steam methane reformers. They're all double fired in some way or another. It means there's a flame on both sides of the tubes. They're all gas fired. Process outlet temperatures are relatively high compared to refining fired heaters, and the radiant heat flux is also quite high. And I apologize it's in BTUs per hour because I'm sitting here in the United States, and you know what the Americans are like for changing over to the metric system. There's no coking tendency inside the tubes. The tube metallurgy is a nickel chrome alloy of some sort, and the catalyst is actually inside the tubes, and it's a nickel-based catalyst. Because the tubes are a nickel chrome alloy, there's little tendency for scale formation. They do oxidize, but they form a very thin oxide layer, and typically once that oxide layer is formed, there's very little further oxidation taking place. So is this a good candidate for CTEC? Well, yes, it is, but we have to be careful. Tube coatings are not applicable because what we do with the tube coatings in refinery fired heaters is stop scale formation and growth. Since these are high alloy tubes, there's no scale formation, so there's really no point in coating the tubes. The oxide layer that forms on the surface of the tubes is a high emissivity oxide, so putting a high emissivity coating on is certainly not going to help anything other than cost our customers money, which is totally wasted. The refractory coating Yes, it's good, but there are some concerns that we have regarding the duty balance between the radiant section and the convection section. And I mentioned online services, our hot tech services. They're good, especially for HCC and CCC, which are hot convection cleaning and cold convection cleaning. So, and we also have a service which we call HRR, which is hot refractory repair. So if you have any refractory problems in your steam methane reformer, we can address those while you're still operating. No need to go down. So let's continue. This is just a summary slide of what we offer with the refractory coatings. Here on the right-hand side, you can see it's like looking at the star or a black cat at night. You know, you don't really see too much. But on the left-hand picture, you can see there's a spray gun just out of picture. He's spraying just above the wall-mounted burner. And that's a brick-lined furnace. The right-hand side is a similar shot. Refractory coating pictures tend to be very boring because it's like looking at, like I said, just a black picture. We use these coatings in gas-fired units only, and I'll explain why later on. In ceramic fiber lined units, we increase the emissivity from 0.45 to about 0.92. All of our coatings, tube refractory coatings, which are high emissivity coatings, have an emissivity of 0.92. That's about as high as you can get using refractory materials. We apply the refractory coatings to all the available surfaces to try to create as near as possible a black body enclosure. And typically the benefit from that is to increase the radiant heat transfer efficiency by up to 5%. Because the refractory surfaces are radiating heat within the enclosure, the heat flux is not a lot more uniform. If in a low emissivity enclosure, you tend to get a lot of reflected heat from the flames. So it tends to be concentrated in certain areas within the unit. Because we're making the heat exchange more efficient, we tend to end up with lower bridge wall temperatures and lower stack temperatures. And sometimes that can lead to problems, especially if you're using the convection section for process preheat or steam production. In a steam methane reformer, we have to be very careful. So you can see at the bottom there, an evaluation of the impact on the convection section is very important. And that's why we like to do an evaluation before we undertake any application that we make. This is just a chart showing the emissivities of various refractory materials. Starting from the right-hand side, you can see ceramic fiber, 0.45. Insulating brake and castables are around 0.6, 0.65. And the C-Tech refractory coatings are around 0.92. So let's look at a little bit of theory and see if we can understand how the coatings actually work. You can see on the left a schematic of a refractory line box with some tubes in. And the A1, T1, and E1 are the area, temperature, and emissivity of the refractory lining. And A2, T2, and E2 are the area, temperature, and emissivity of the tubes inside there. So Lobo and Evans and some others used a Stefan Boltzmann equation as a basis for creating an equation for heat transfer from the refractory to the load inside a furnace. And they came up with that equation where QR equals the function divided by F. The function is obviously the Stefan Boltzmann equation with T to the fourth functions inside there. F is the interesting thing. We have to keep that factor as low as possible to maximize the radiant heat passing from the wall to the tubes. And you can see underneath F is equal to, again, another equation based on surface areas and emissivities. And if you scan down to the bottom, the first example would be for a ceramic fiber lined unit, where E1 is 0.45, E2, the surface emissivity of the tubes, is 0.88. And we're assuming that the surface area of the refractory in the tubes is the same, just for simplicity. Here, the factor would be 2.35. And in the bottom example, all we've changed is the emissivity of the refractory. We've made it 0.92, and because we coated it. And that works out to be a factor F equals 1.22, which is approximately half of the example 1. So clearly, if you go back to the top equation, QR would be double the amount of heat coming from the walls to the tubes. I emphasize that it's just the heat going from the walls to the tubes. So let's move on to the next slide. Here we are showing a similar schematic, but bottom fired with, you see where the flames are from the burners. And the radiation obviously goes in all directions. Most of it will go directly to the tubes. Some of it will go to the refractory, and then from the refractory surface to the tubes. The high emissivity coating has no effect on the radiation going directly from the flames or the flue gases to the tubes. It only has an effect on that going from the refractory surface to the tubes. So instead of getting a 50% increase in radiant heat flux, we get something like a 5%, because the wall has a lesser effect than the direct radiation from the flames and the flue gases. This next one is a schematic showing a top-fired unit. There are many top-fired Kellogg design, KTI design units which have top-fired burners. Here you could see that the refractory coating on the side walls has an effect mostly on the tubes nearest to the wall. But as you go further inside the unit, the effect from the high emissivity coating on the side walls diminishes because the tubes shield themselves. And so the tubes in the center would get very little effect. The only effect is from the roof around the burners. So the effect from coating the refractory lining in a top-fired unit is a little bit less than the Foster Wheeler or the Howler Topso units. Same. This is a radiation spectrum, just showing the difference between a gas-fired flame, which are the red and blue peaks inside there. They're the combustion products of natural gas when it burns. And you can see that below 4 microns, which is where most of the heat and radiant heat transfer takes place, it's basically just one narrow waveband transferring the energy. So that's the emission spectrum. Oh, excuse me, and also the absorption spectrum. The envelope around the outside is the spectrum for a black body at the same sort of temperature. And what we're trying to do is make the gas-fired radiation, we're changing it into a black body radiation, because the high emissivity coating will absorb and then re-emit radiation in that form, in the black body form, or almost black body form, into the unit, which is a much more efficient way of transferring heat. The reason that the coating, the high emissivity coating, is not used in oil-fired heaters is that this area underneath the envelope curve is more or less filled with different peaks. So the oil flame, the oil-fired flame, and the radiation from it is very close to black body in the first place. So there's very little improvement in using a high emissivity coating in an oil-fired unit. So the typical benefits and consequences of improved radiant heat transfer. We get an increased radiant absorbed duty for the amount of energy that's consumed, efficiency. So we can use that improvement in efficiency for increasing the production rate without increasing firing, or we can save energy. We can save the fuel consumed for producing the same amount of product. We get a much more uniform heat transfer. And in a ceramic fiber lined unit, the coatings are much more durable than the friable ceramic fiber surface. So we encapsulate the ceramic fiber, and there's no loss of the fiber downstream to the convection section or SCR units if you have them. Because we're absorbing more heat in the radiant section, the bridge wall temperature, the flue gas temperatures are lower. Also, the NOx emissions, which are related to flue gas temperatures, are also reduced. And we typically find, or our customers report to us, that after coating an SMR unit, we get something like 20 to 30% reduction in NOx emission. A few of our customers have just applied coatings just to get the NOx emission reduction. The duty is lower to the convection section, and again, it's important to do an evaluation because of that. So the typical operating constraints that the coatings can address are high bridge wall temperatures, high temperatures in the convection section, which puts strain on the coils there, especially the fins, and also the support structure in the convection section. Also, if you're operating and you've maxed out on your burners, the coatings will allow you to cut back on the burners a little bit or use a little bit more space there. So primary benefits, improved thermal efficiency, reduction in bridge wall temperature. We mitigate high temperature problems in the convection section. There's a flexibility to change the firing profile by manipulating the heat flux inside the unit, and we can increase production or save energy, save fuel. The secondary benefits, I apologize, this slide's a little busy, but we can preserve the furnace lining, the ceramic fiber especially, from the hot gas abrasion, which removes the friable surface of the ceramic fiber and deposits it in the convection section or SCR units later on. It will also potentially be deposited on the radiant section tubes, which will not only insulate them to a little degree, but also making tube metal temperature measurements more difficult. So the lack of that fibery coating on the tubes will allow the measurement by infrared thermography, for instance, and be much more reliable. We have, if you're only interested in encapsulating the ceramic fiber, we have a neutral emissivity ceramic coating, which we can use if you're happy with the heat transfer characteristics inside the unit. In the SCR unit, the elimination of screen or catalyst fouling allows maximum efficiency in NOx emission reduction there. Okay, and we reduce NOx emission, as I mentioned before. So, a couple of case studies here. This first case study is for a Foster Wheeler designed terrace wall, single cell reformer. The convection section consisted of mixed feed, steam generation, steam superheat, and BFW, boiler feed water preheat. There was actually auxiliary firing in the convection section in this unit. Furnace draft was okay. Stack temperature was quite good. So we sent 6 technicians. They worked one shift per day, one 12-hour shift per day. They cleaned the refractory by wire brushing the castable or brick inside the unit. And we cleaned the ceramic fiber with a nylon brush. You'll see flattening there, the ceramic fiber. The ceramic fiber modules tend to be rippled on the surface when they're new. After we've cleaned the friable fiber away from the surface, they tend to be a little flatter rather than rippled. So there's less of a corrugated surface on the fiber. The dust that we generated was we blow it down inside the unit and then vacuum it up. We put plastic sheeting to protect the reformer tubes, the catalyst tubes, from overspray so that they remain clean. The ceramic fiber, we apply a rigidizer first, and then we put a R371 coating on top. And the brick was coated with a base layer of R360 and then a top coat of R370. These are typical materials that we use in refractory linings in high temperature units. The whole coating application, we occupied the unit for 3 days. So the results, you'll see there that the gas usage came down by 600 gigajoules per day, but while we were celebrating, they told us that 250 gigajoules per day of that came from the replacement of steam superheat coil. So it was calculated that 350 or 360, sorry, gigajoules per day came from the coating, which was about 4% reduction, which was what we'd estimated in the first place in our evaluation. We also reduced the bridge wall temperature by a very nice amount, since more heat was now being absorbed in the radiant section. The steam generation from the convection section was slightly reduced, but it didn't have any impact on the plant steam balance. They were still happy with that result. So another case study here. This was a Halder Topsoe unit. They'd had high bridge wall temperatures from the beginning, or high flue gas temperatures to the downstream coils that were actually close to design. We applied the ceramic coating in 2007 plant turnaround. The bridge wall temperatures dropped by about 40 degrees C or 70 degrees Fahrenheit. And the fuel efficiency was improved overall by about 2%. They found that they could also use the benefit to increase the production rate by 2% as they required. We reapplied the coating in 2011 as some deterioration was noticed. And you'll see that in a chart I'll show later on. This is the condition of the coating after the first 4 years. All looks in very good condition. The white lines are where the fiber modules have shrunk during the cool down, which is perfectly normal. This is another shot looking down the sidewall. You can see the flat flame burners in the wall. Now this is the chart that shows the flue gas temperature outlet in degrees centigrade. I'm looking here. This is when we applied the coating in 2007. The flue gas temperature started off at about 940, 935, but dropped significantly to around 890. But then in use, it started to creep up. There was a turnaround in 2008. After that, things stabilized, and after the turnaround in 2010, the flue gas temperature started to increase again. And in 2011, they went down and we recoated the unit, or touched up the unit. And then it was up until 2012, which is all the numbers I have, the performance was fairly stable. Case study 3, getting close to the end. This is another Haldor-Topsoe steam methane reformer with 2 cells, ceramic fiber and brick lining, wall-mounted burners, of course, with vertical tubes. The coating objectives were fuel savings mainly. This was some time ago when natural gas cost a lot of money. They wanted to lower NOx reduction and CO2 as well. And they'd known about our ability to prevent convection section fouling, so they were most interested in that as well. These are the results. On the right-hand side, the chart shows that fuel consumption at 90% capacity came down to, was reduced by 3.5%. CO2 emission reduction was around 3%. NOx emission reduction, I measured at 20.9%. And flue gas temperature in the stack came down by 8%. They noticed a much more uniform heat flux. And on the left-hand side, you can see the commercial aspects of this application. The cost was about 150,000 euros with an annual fuel saving of almost 450,000 euros. So the payback on fuel reduction was around 4 months, and the estimated return on investment was about 18 times over the coating life of 6 to 8 years estimated. So they were very happy with those results, as anybody should. I've mentioned a couple of times that an evaluation is very worthwhile, and we offer a complimentary fired heater evaluation with every application that we do, which means that we'll pester our customers for data. For a steam methane reformer, that would just be design specifications and current operating conditions, and some general arrangement drawings as well. Then we'd use that data so that could be done remotely. These days, that's quite important. There's no need for us to actually visit sites. So long as you're happy to fill out a questionnaire with current operating data, then it works very well. We use that data, then simulate the performance before the coating application, and then we can provide you with an estimation of the impact of the ceramic coating on the performance. And that will give you an efficiency improvement number, which you could use as a fuel saving estimate or a production increase estimate. Okay, well, that's the end of the presentation, a fairly short one. So if you've any questions, we'd be very happy, as Marina said earlier, to receive them. And I'll stay around here to answer them as best I can.
Well, John, you'll be happy to know that we have quite a lot of questions already.
Uh-oh.
So we'll go right in. So our
Okay.
first question is from Adnan. In primary reformer refractory is more than 20 years old. In this case, would the thermal emissivity coating be effective or not?
Well, we'll increase the emissivity, yeah, whatever condition or whatever the age of the refractory. But we'd like to have a sound base to apply the coating to. So the first thing we do whenever we go inside a unit is look at the condition of the refractory. If we feel that it's good enough after cleaning to apply the coating, then we'll go ahead. But if we come across a unit that the refractory condition is so poor that it wouldn't give us sound base to put the coating on, we'll mention that to the customer and then ask them either to acknowledge the fact or repair it before we make the application.
Thank you, John. Our next question from Ahmed. Do we have any references in ammonia plants?
We've, yes, done a few applications in ammonia plants. A lot of our customers are not too happy about giving away formal references, but yes, we can provide references if you contact the local account executive that we have there. I'm sure we can provide references. We've got a lot. What we tend to provide is an experience list, which would be companies that have used our coating technology.
Mm-hmm. Thank you, John. Next question from Quasi. What is the life of this high emissivity refractory coating, and how often do we need to apply it?
Well, you'll have seen in the case study there, the emissivity, or rather the flue gas temperature on the chart increased again after about 4 years. That's not typical. We generally recommend in the steam methane reformers that the coating is either touched up or reapplied after 6 to 8 years. 4 years is extreme, and it depends on the duty inside the unit, how hard the unit's being fired. But 6 to 8 years is a typical number for a steam methane reformer. In a more gentle refinery fired heater, we can get around 10 years or more.
Thank you, John. Another question on references from Amit this time. Do we have any references for such coatings in steam cracking furnaces?
Steam cracking furnaces, we've not done a lot in ethylene furnaces. We started off in ethylene and had a few inconsistent results, and mainly not because of the performance of the coating. The coating works very, very well. But in ethylene furnaces, there's a lot of duty, similar to steam methane, but even more so, a lot of duty in the convection sections. And we found that the benefit we were giving in the radiant section, we were losing in the convection section. Also, in ethylene furnaces, you tend to have a bank of about, 8, 10, 12 ethylene furnaces in a row. And the whole bank of furnaces, there's one gas meter to measure the fuel consumption over the whole bank, rather than each furnace being individually measured. So it's very difficult for customers to measure the benefit.
Thank you, John. Next question from Afan. How can we calculate the spring hanger or weight balance of reformers' tubes in order to maintain expansion and contraction of the tubes during startup and shutdown?
How can you? I've got no idea how you can measure the weight. The
weight balance, or
the weight balance. No idea. Outside my experience, that's a question for a furnace manufacturer or designer, not really related to coatings.
And we can refer you to some of the furnace manufacturers because we work very closely with them, right, John?
Right, absolutely. Halda Topsoe or Foster Wheeler or the designers, they will be able to tell you how to do that.
So if you let us know, Afan, which designer you would like to speak to, we can provide a reference.
Sure.
Next question from Kazi. We found a lot of dust in our convection section, sidewall furnace. By applying this coating, can it help in reducing the dust in convection section?
Sure, that's one of the secondary benefits that I mentioned a couple of times. The ceramic coating will encapsulate the ceramic fiber or the brick or the castable material inside the radiant section. So there's much less carryover of dust that's generated from the refractory. If you're in an environment where it's very dusty outside, that dust will be pulled in through the burners or through where the air comes in, and there's not a lot we can do to mitigate that, unfortunately. But anything that's generated from the refractory lining, yes, we can certainly reduce that. We can also clean the convection section if online, if there's a need to do that between coating applications or between shutdowns.
Thank you, John. And we can talk to you more about convection section cleaning. We do have another webinar coming up in a few weeks' time focused on online fired heater services. We'll send you all a link to that later. And next question we'll take from Rana. In case of ceramic coating, can we measure tube metal temperatures in primary reformer?
Yeah, as I mentioned, we don't put the coating on the tubes in the primary reformer. There's no benefit from doing that. So you would measure the tube metal temperature in the normal way. So we have no effect on that. We don't put coatings on the tubes.
Thank you, John. Next question from Alexander. In top fire reformer, how does the ceramic coating improve the heat uniformity? I feel like it will have the opposite effect.
It doesn't have the opposite effect. As I mentioned during the talk, a top-fired reformer is not the best design for using the benefit from the coatings, mainly because the center tubes are shielded from the radiation, which is affected by the coating on the walls. So it's a lesser. There's less benefit.
Thank you, John. Next question from Adnan. How long does the coating last in a steam methane reformer?
Yeah, typically 4, 6, 8 years, depending on the how hard the unit's being used and how much flame impingement. The more flame impingement, the shorter the life. But there's certainly a benefit, and you can see in the benefit in the last case study that we had, the payback on the benefit was about 4 months. So even if the performance is as short as 4 years, you've still got a whole load of return on your investment. It's very much worthwhile.
Thank you, John. We have another question on the coating lifetime from Marcella, and I guess the answer would be the same. It depends. Yep. 4, 6, 8 years.
Right.
Next question from Mohammed. Because of the coating, will it take more time to heat up the reformer during startup, as it will consume more fuel gas and result in excessive time?
No, the ceramic coating will help to have a more uniform heat up in the radiant section. It doesn't take any longer. The coatings are very thin, so they don't add to the thermal mass at all in the radiant section. So it really doesn't have a detrimental effect on the heat up. You'd have to use whatever heat up schedule or scheme that the refractory manufacturer recommends anyway. So the coatings don't really have too much of an effect, other than making the heat up more uniform.
Thank you, John. Next question from Onur. Do you also perform CFD simulation after the coating application?
We perform an evaluation before and after, yes.
And another question from Rana. Would you recommend to apply a 20-year-old refractory Z blocks in a primary reformer?
Yeah, it depends on the condition. As I mentioned earlier, we look very closely at the condition of the surface of the Z blocks after cleaning, and if during cleaning it's very, very poor, then we'd recommend to the customer that they're changed out.
Yes, thank you, John. Another question on the condition of the refractory. Do we perform a survey of the refractory condition before suggesting a coating?
It's very difficult to do a refractory condition survey during operation. Typically, we look at the unit while it's firing and collect data while it's firing. And the first time we get to look inside is when we go in to apply the coating. Now, if the customer knows that there's some refractory issues inside the unit, it's better for him to address those before we go inside.
Thank you, John. Next question from Hyrule. How does this coating affect the external temperature of the SMR box?
As I said, it's a very, very thin coating, so it doesn't add to the thermal mass nor to the insulating value of the refractory. And the external temperature is related to the thermal conductivity of the refractory lining more than anything. If you're able to use the ceramic coatings to save fuel, then you'd be firing less, maybe up to 5% less, which means that the flue gas temperature inside the unit would be lower. So from that aspect only, the external temperature would be lower as well. There's nothing too sophisticated about it, other than if you reduce the inside temperature, yes, you might get an external temperature reduction as well.
Thank you, John. Next question from Ghulam. How much time will it take to apply on a tube feet height in a side-fired steam reformer?
Depends on the size. You saw before that in one application in a Halder Topso unit, I think, or was it the Foster Wheeler unit? We sent a crew in of 6 people working 12-hour shifts, and we were there for 3 days. So refractory coatings don't take too long for us to do. If it's a large unit, we'd send 2 crews working round the clock and to get the work done as quickly as possible. Normally the turnaround people are very protective of the time that they have inside the unit. And we'll work with the turnaround management to fit in with whatever time they make available.
Thank you, John. Question from Jorge. Do you have any reference benefits on the tube life?
Tube life, like I said, we don't put coating on the tubes, so we don't affect the tube life. In refinery-fired heaters, where they use a steel alloy tube, not a nickel chrome tube, we do put coatings on those and stop oxidation altogether. And yes, that will increase tube life. If the coating lasts for 10 years in a refinery-fired heater, then we probably extend the tube life by 10 years. But in steam methane reformers, we don't apply coatings to the tubes, so that's not an issue.
Mm-hmm. Thank you, John. Next question from Ghulam. Is this coating so beneficial? Do designers use this coating in latest designed reformers?
No, we do work with one fired heater designer, and they do recommend ceramic coatings inside their units, both for the tubes and for the refractory. That you'll see is for refinery-fired heaters, not for steam methane reformers so far.
So we may work with more in the future. Is that what we're saying?
Possibly. Depends what agreements we can come to.
Thank you for that. Question from Zahaib. By ceramic coating, we get uniform heat transfer. Could you please explain that?
Yeah, if you think of an extreme situation where the refractory lining is a very, very low emissivity, so the walls would act like mirrors and they'd reflect the radiation around inside the unit. So if you've got flames at the bottom, if you imagine a light bulb at the bottom, it would reflect from the sidewall mirrors onto the bottom tubes only. So that's where most of the radiation would strike the tubes from a very low emissivity lining. If you put a black body coating on the lining, the black body coating absorbs all the radiation and then re-emits it, but it re-emits it in all directions. It's not like a reflected light or radiation from a mirror. So it goes in all directions, and that's why the radiation is much more uniform in a black body.
Thank you, John. Explained this very well. Next question from Atul. What's the curing time and the number of layers required, and what are our requirements on site to carry out the job?
The curing time is very quick. It dries very quickly. The curing is taken care of by the first firing of the fired heater or the reformer, and there's no specific heat up schedule that the coating would require other than that recommended for the refractory. I've forgotten the last part of that question. What was that?
What are our requirements on site to carry out the job?
Obviously, full access to the inside of the reformer. We ask the customer to provide scaffolding, and that's about it. We'd like to have services like electricity, water, compressed air. If the customer can provide that, that's exceptional. Otherwise, we can provide that ourselves. But typically, working around the world, the customer knows the suppliers and has deals with the suppliers of those units that we don't. So it's less expensive for him to get them directly.
Thank you, John. And you'll enjoy this question from Adnan. After the application, what is the performance guarantee?
Depends on the evaluation. If we go in and do an evaluation beforehand and find that we get, I don't know, say 5% benefit, we would provide a performance guarantee in some cases for maybe 70% of that benefit. And that would depend on the post-application evaluation that we do as well.
Thank you, John. We'll go and address some questions in the chat as well. So we have a question from Rajesh. Do you carry out survey of the refractory before suggesting the coating?
Yeah, I answered
you
that
addressed
already.
that. You have answered that before. We have a question from Charles. When will the Hot Tech webinar be? It will be very soon, and you will get a link to it in the chat later today, and also in an email when you get this webinar recording. Question from Dan. How is the coating applied, and will it contaminate the tubes?
It's applied by spray. I think most of the coatings are applied by airless spray, which is obviously creates less problem inside the atmosphere. But we go to great lengths to protect the tubes. In some cases, we hang big plastic sheets down on both sides of the tubes. If that's not applicable, then we'll wrap individual tubes just to make sure that they're protected from the coating overspray.
Thank you, John. And I see a few more questions about the tube life. I suppose this is in reference to other fired heaters where we would do both the tubes and the refractory. And we do have another webinar, coincidentally, on the topic next week. I will post a link to it in the chat and send it to you by email also.
Okay.
Question from Charles. Have we ever done any work at Sasol, South Africa, Secunda gas reforming?
We've worked in Sasol. In fact, I think we're looking at doing a job fairly soon in Sasol, depending on the economics. I know Sasol are going through a pretty hard time at the moment, but yes, we've certainly worked in Sasol. In the refinery, on the, I think the catalytic reformers there, maybe a crude or a vacuum furnace. I can't remember.
We'll make sure to get back to you with the specific reference, Charles. Question from Mohammed. Will this coating decrease the tube metal temperatures?
Really, the tube metal temperature is related to the process going on inside. You have to get the inside metal surface to a certain temperature to heat up whatever's going through the tubes. So really, it has very little effect on the tube metal temperature. On the surface temperature, if we're applying a coating to eliminate scale formation on the tube, like in a refinery fired heater, if you're measuring the surface temperature, yeah, we reduce the surface temperature quite a lot. But the surface temperature isn't the metal temperature. The surface temperature is the temperature of the scale. And it could be 200 or 300 degrees higher than the metal temperature. But in the process of applying the coating, we remove all the oxide, all the scale from the surface. We take the tube down to a white metal finish, and then put the coating on that. The coating is very thin, so it's a significant reduction in surface temperature, not metal temperature.
Thank you. Next question from Abid. By what ratio can we save fuel by applying this coating?
Well, I mentioned before, up to 5%. If it's below, say, 2%, it's not really economically viable. So normally we say we provide between 2 and 5% benefit, or 2.5 and 5%.
So would that be the average?
Yes.
Question from Ahmed. What is the performance criteria to evaluate this procedure, and what is the time required to implement this?
Well, performance criteria is a measurement of improvement in efficiency of the unit, of radiant efficiency. That can be measured by bridge wall temperature reduction, or by fuel saving, or by improvement in production rate. So all those criteria have been used to justify the application. What was the last part?
And what is the time required to implement this?
Yeah, time depends on how big the unit is. And it's totally related to the surface area of the refractory that we're treating. But 3 days to a week, maybe.
Mm-hmm. Thank you, John. And as we keep talking about how can we measure or predict the benefit, we're not finished with the webinar yet, but I'll just post a link to the survey. As a token of our appreciation to the attendees, we're offering a complimentary evaluation in 2020. So if you'd like us to evaluate your SMR to see if there would be a benefit, then you're welcome to let us know if that would be of interest, and we would get back to you with more information on what information we would need to calculate that.
Yeah, but with an SMR, we don't need to come to site, so there's no hazard these days in moving around. We can do that, from from our home base, just so long as we get the data from you.
Thank you, John. Next question from Dan. Have you ever applied the coating in the convection section of a primary reformer in an ammonia plant where tunnel burners exist?
No, is the easy answer to that. We've not applied coatings in any convection section.
Is there a reason for that?
Normally, they're very tight bundles of tubes with finned tubes. Difficult to get in there to give a uniform coating. So it's it's virtually impossible.
And we had a follow-up question. In case we had applied coatings in the convection section, references would be appreciated, but we don't.
No.
Let's have a look if we got any more questions in the questions tab. Question from Rana. Does the coating life depend on the number of shutdowns of a reformer?
No, not really. You'll have seen in the photographs from the Halter topsoil unit that the fiber modules did tend to shrink, and there was a crack in the coating between the modules. But on heat up again, that crack disappears. The coating normally survives much worse thermal shock than the heat up shutdown or shutdown heat up cycle that the unit has to go through. So no, there's no effect on coating life.
Thank you, John. And a rephrased question from Jorge with regards to tube life. If we don't apply any coating to the tube life, but just the fact that we applied the coating onto a refractory, would that improve the tube life?
Well, you're making the heat flux more uniform, so I suppose you're reducing the hot spots on the tubes, so it could well improve the tube life from that aspect alone, yes.
I suppose it's not something we have measured.
No.
But it's possible.
Yes, certainly.
If John says it's possible, it's definitely possible.
The oracle has spoken, yeah.
Yes.
If you believe that.
Oh, we believe everything you say, John. Next question from Zohaib. TMT of the tubes will increase.
No, not necessarily. Not unless you go for a higher throughput. Obviously, a higher throughput, you'll need to heat up more processed fluid per unit time. So the tube metal temperature would have to increase slightly. So yeah, I mean, it depends on the processing, but the coating in itself doesn't necessarily increase the tube metal temperature. Like I said in the previous question, if you're making a more uniform heat flux within the units, you might actually reduce the peak metal temperature in some areas.
Thank you, John. We have another question from Charles. Have you ever done hot tech online cleaning on convection sections at any Sasol South Africa business units?
Oh, maybe. I can get back to you. I'm not sure. We've used convection section cleaning quite often around the world. I don't have a list in front of me at the moment, so sorry. I'm pretty sure we've talked about it. I can't remember whether it's been done.
It's all right, we'll get back to you on that. Question from Abid. What would be the effect of applying the ceramic coating on stack temperature?
It's if you use the ceramic coating to reduce fuel consumption, it will reduce stack temperature in the same way that it reduces the convection section temperature, because you're absorbing more duty in the radiant section. The flue gas temperatures will be lower. I think in one of the case studies, you might have seen that the stack temperature came down by 8 degrees centigrade. So not a whole lot of reduction, but a significant reduction for a stack temperature.
Thank you, John. I think that was our final question. Well, I would just like to thank you very much for this excellent presentation and for doing the Q&A. And I'm sure our audience will agree. There is one more question that I hope you can take
Oh,
from,
sure.
from Honor. I'll zoom you in. Is there any effect on O2 level on the stack?
There may be an improvement in draft, but oxygen level, I'm not sure. That's more to do with combustion and getting a more complete combustion in the radiant section. We may affect that, but I don't know.
Okay, thank you for that. So that was our last question. I would like to thank you all for attending. And as I mentioned before, we do appreciate you taking the time to listen to us today. So do fill in the survey, let us know how we've done, and you're welcome to express your interest in a complimentary SMR evaluation this year.
Yes, thanks very much, everybody.
Thank you very much, and have a lovely day.
Thanks, Marina.